Welcome to today's SCA webinar with Dr. Steve Sonnenberg on geologic carbon capture, utilization, and storage. Before we start today's webinar, we'd like to ask the audience a few questions so we can learn about the demographics. So let me launch the poll. And the first question is, what is your primary discipline? We're starting to get answers from the audience now. It looks like we have quite a few geoscientists in the audience and quite a few petroleum engineers, a few in the other category in facility engineering. Votes are still coming in. So it looks like most of you have voted. So I'm going to go ahead and close and share the results. 62% are geoscience, followed by 26% in petroleum engineering. So our next polling question is, how many years of full-time experience do you have in the upstream oil and gas industry? So we're collecting responses. Looks like quite a few are in the middle category in the 11 to 20 year range. And good percentage in the 21 to 30 years and a fair percentage over 30 years of experience. And most of you have voted now, so I'm going to go ahead and close the poll and share the results. We have 42% in the 11 to 20 year range, followed by 27% with over 30 years of experience. So let me go ahead and share my desktop. And before I introduce Dr. Steve Sonnenberg, I'd like to remind the audience that you're muted today, but you can ask questions using the GoToWebinar question feature. We'll cover the Q&A at the end of the presentation, and you will be anonymous. This webinar is Geologic Carbon Capture, Utilization, and Storage. And our presenter today is Dr. Steve Sonnenberg. Steve holds the Charles Boettcher Distinguished Chair in Petroleum Geology at the Colorado School of Mines. And he's a native of Montana and received degrees in from Texas A&M and Colorado School of Mines. So several locations covered there. He has over 25 years experience in the industry and has also been teaching at Colorado School of Mines for a number of years. Steve has been a president of several oil and gas organizations, including APG, a number of other ones. And he's also been involved in the Colorado Conservation Commission for Oil and Gas and was chair in 1999 to 2003. He's received a number of awards from APG, including the Halibuty Medal in 2013. Steve teaches several courses for SCA. The one we're featuring today is the Carbon Capture, Utilization, and Storage, and it's a geological perspective. He also teaches the elements of petroleum geology, reservoir characterization for bedrock reservoirs, and unconventional resource plays. So the carbon capture course will be taught in a live online format virtually in late April, April 25th to 28th. That'll be mornings. So for whatever part of the world you're coming from, that may be convenient for you. Half days for 4 days. There are a number of other classes that Steve teaches. You can certainly look at our website to find out when those are scheduled, or perhaps you'd like to schedule one of his courses in-house, so we can work with you on that if you'd like. We have several online classes that are coming up. Just around the corner, we have Michael Perch from University of Texas teaching subsurface machine learning. Dr. John Lee from Texas A&M is teaching production forecasting for low permeability reservoirs. And Dr. Christina Economides and Dr. Demetrios Hazignatou are teaching the engineering perspective on carbon capture, utilization, and storage. And that's offered live online in the mornings in mid-March, and it's being held in person in Houston in June. We have some free webinars like this one that are just around the corner. We have Bob Barbet speaking on refracking organic shale wells. That's February 16th. And we have Dr. Rebello Samuel talking about optimization with respect to drilling. Looking forward to that opportunity. That's in March. So don't forget about SCA, not only for training, but also for consulting, for direct hire, for both contingent labor and full-time resources, and also for projects and studies. And so without further ado, I'm going to pass the presentation rights to you, Steve. And you can start your presentation.
Okay, well, let me get this screen switched. Hopefully everybody can see the screen.
Yes.
And hopefully everyone can hear me. I want to thank everybody for your attendance this morning. It's 11 o'clock in the Denver area if you're from the Houston area or elsewhere, of course, different time zones. And you're in your lunch hour, for some of you anyway. So today we're going to emphasize the geology associated with CCUS and some of the ways in which we can accomplish carbon capture. And then we'll go into greater detail on that in the upcoming course too. So very briefly, just as an introduction, a little bit about greenhouse gases, CCUS, some chemical, physical considerations. Some CO2 phase behavior, and then some mineral reactions, which one should also keep in mind. I think we're all well aware of the greenhouse gases, CO2, methane, nitrous oxide, also known as laughing gas being the primary ones, and CO2, which is the majority of the greenhouse gases, is the subject of today's meeting. Has a number of different sources that generate CO2, and the idea is how can we end up capturing that. So the idea of CO2 capture has been around for a while. Shell Oil Company and their website had this slide, and it must be at least 10 years old now, but appropriate for our lecture today, capturing CO2. So CCUS options, there's the terrestrial sequestration, that's more of the natural sequestration that goes on. And then we have these opportunities for geologic sequestration of CO2, injection into depleted marginal oil and gas reservoirs, doing enhanced oil recovery or enhanced gas recovery, can also do enhanced coal bed methane recovery, all of these using CO2, of course, enhanced shale gas recovery using CO2, CO2 injection into deep unminable coal seams, enhanced geothermal systems instead of using just hot water, or can use CO2 or a combination of hot water and CO2, and then CO2 injection into deep saline aquifer reservoirs, which is a hot topic today. And then there's the mineralization ideas also going around. So this slide kind of captures that previous list, showing all the storage options, storage and or sequestration options that one then would have for CO2. So chemical, geochemical and physical considerations, miscible, immiscible displacement of native fluids. CO2 can be miscible and immiscible with oil, and probably the same comment could come up with some of the deeper injection. There's also the dissolution of injected fluids into reservoir fluids, meaning that's mainly for EOR opportunities. One has to consider injection and injection pressure, and hopefully not induce any seismic activity. Chemical interactions between injected fluids and aquifer fluids, and injected fluids and solids, also something to be taking into consideration. So CO2 phase behavior, geologic sequestration and CO2 in saline aquifers would be preferentially occur at supercritical conditions. And CO2 becomes supercritical at temperatures greater than 90 degrees Fahrenheit and 1,000 psi. Supercritical CO2 has a high density like a liquid, but moves like a gas. Supercritical CO2 has a density ranging from 500 kilograms per cubic meter to over 800 kilograms per cubic meter. Density of CO2 stored underground depends on pressure, temperature, of course, and then supercritical CO2 is preferred because it's denser, takes up less space than gaseous CO2. So a phase diagram, anybody that's been messing around with CO2 as of late probably has this memorized, but different pressures and temperatures and the different states that CO2 occurs in, from solid to liquid to gaseous state, and then the supercritical state illustrated in the upper right-hand portion of the slide. In general, CO2 is carried in pipelines in liquid state, and then for CCS purposes or EOR purposes, the CO2 in general is in that supercritical state. And I'm sure there's exceptions to what I just said there. Can also look at this diagram that illustrates the volumes of CO2 as they are put into the subsurface. And you start out with this number in the atmosphere, 100, and by the time we get down to 2.5 kilometers, you can see the number in blue, 0.27. So the blue numbers show the volume of CO2 at each depth compared to the volume of 100 at the surface, and that just shows you how much smaller the space is required when we get to much greater depths. There's tends to be this magic depth threshold at about 800 meters, 2,600 feet, 3,000 feet, let's just call it, where we can go into supercritical conditions for CO2. So a lot of what we talk about today, the suggestion is to be below 3,000 feet in whatever activity is that you're doing if you want to be in supercritical CO2 phase diagram area. Also shown on this slide is the density of CO2, and you can see that changing density as we get into the deeper subsurface and approaching gradients, if you would, of like 0.7 gram per cubic centimeter, or the density, I shouldn't say gradient, 0.7 grams per cubic centimeter as we get to the greater depths, 2.5 kilometers. Also, which is important, is considerations of CO2 solubility in water at various temperatures as a function of pressure. CO2 solubility increases rapidly from pressures of 0 up to about 1,500 psi, then increases much more slowly. Also, CO2 is more soluble at lower temperatures. Solubility, if conditions in the reservoir aquifer do not allow CO2 to persist in supercritical state, some of that CO2 is going to go into solution. CO2 solubility, again, increases, as I previously stated, rapidly up from 0 to 1,500 psi and then more slowly thereafter. CO2 is more soluble at lower temperatures. Pure water has a greater solubility of CO2 than saline fluids. Just to remind you of the saline fluids that we deal with in the subsurface, these brines typically have salinities that are much greater than seawater, and it's not unusual to see parts per million numbers of 100,000 to 200,000 associated with some of the brines that would be injected into for deep saline aquifer sequestration. Some mineral reactions, very simple on this diagram to keep in mind. CO2 dissolves in formation water, forms carbonic acid. 1% of the dissolved CO2 exists as carbonic acid. We also create bicarbonate, and the lower formulas illustrate how bicarbonate can react with either calcium or magnesium and precipitate our favorite minerals, limestone or dolomite, in the deep deeper subsurface, we can also go through dissolution phases as indicated by these formulas too. So CO2 and the interaction with reservoir rocks, and then the possibility of precipitation of minerals is of great research interest. Other thing to take into account is the possibility of induced seismicity due to fluid injection, and probably the classic case of fluid injection in a waste disposal well, not related to fracking, happened in the Denver Rocky Mountain Arsenal well. Well was drilled in 1961, injection of wastewater in 1962. Millions of barrels injected, 710 earthquakes occurred during 1962 to 65. David Evans's diagrams on the left-hand part of this slide illustrates this relationship that was developed between volumes injected and the frequency of earthquakes, and pretty well demonstrated that there was a cause and effect to those earthquakes. Earthquakes had a magnitude of 0.7 to 4.3 on the Richter scale. So trying to stay below some threshold of where you can induce seismicity is critical, not only for CO2 injection, but for water injection too. And this was wastewater injection in this old Arsenal well. So we'll start working our way down this list. And again, this talk is just an overview of geologic concepts associated with the sequestration or storage of CO2. Of course, CO2 can be injected into depleted or marginal oil and gas reservoirs. They have potential for this carbon storage. They should be screened prior to this happening for proper depth. You also would like to have an anthropogenic source of CO2 readily available. It all involves reservoir characterization, so you need to have a reservoir sufficient porosity, permeability. You have to have a known structural trap, which fields have, and then they also have known seals. So in general, fields can be ideal spots for this CO2 injection to occur, but the size of the prize, as they say, generally has to be big enough to make the economics then work on something like that. So it's the slide that I use in my unconventional class, which shows both conventional and continuous accumulations, and I'm not going to go into any detail on the slide at all, but consider for a minute if some of those oil and gas fields were depleted, they could be then the storage sites for CO2 injection in the depleted reservoirs. So the petroleum system tells us that we have these important elements, and for oil and gas reservoirs of great importance are going to be the reservoir rock, the seal, and the trap that's present. And then we have some other processes that we aren't going to talk about today, but those all have to be taken into account when coming up with a scenario of where and when to do that CO2 storage. So the geologic disposal in these reservoirs deep enough to maintain CO2 at supercritical conditions. I'm going to use this magic depth of 3,000 feet several times in today's talk, and then we can maintain pressures and temperatures at greater than the 1,090 degrees Fahrenheit. And then the density of the CO2 at these pressure temperatures is less than brine water, which facilitates its containment. Switch gears into CO2 EOR. It's been used in the industry for 50 years. US is the leader for CO2 EOR. Most of the CO2 done with EOR comes from naturally occurring deposits. 90%, 10% from anthropogenic sources. And in the future, I think the goal would be to switch those percentages. CO2 EOR operations designed to maximize sweep efficiency. CO2's purchased and recycled during operations. Wells used in CO2 EOR are classified as Class 2 wells by the EPA. So all reservoir lithologies, siliciclastic, carbonate, shales, and others are suitable for CO2 EOR as long as they have interconnected pore space for fluid accumulation and flow. Important geologic factors are rock fluid characteristics, porosity, permeability, structural stratigraphic features that may be present, such as faults, other kind of barriers that may impede oil and gas movement. And then reservoir characterization, of course, is key for all of these studies. So both an engineering and a geologic study ahead of time. So the CO2 Eor process, which is shown by many slides, but all of them tend to look like this: source of CO2 injected into the subsurface, and then that CO2 moves towards the producing well. Generally, the CO2 is injected in alternating cycles with water, so the injection is called a WAG, a water alternating gas injection. The CO2 is miscible with oil. That miscibility increases the volume of oil, also reduces its viscosity, and enables that to flow to the wellbore quite easily. So it's considered a tertiary process, typically applied after water flooding. Incremental recoveries can be 8 to 18% or more, average 12%. Of course, the critical issue is source of CO2, and we're, of course, working and identifying all those kinds of sources these days, as I'm sure you are too. And the critical activities, again, for this to occur, having that deep depth, 3,000 feet, the oil that you're injecting into should be greater than 25 API gravity. Pressure's been maintained through water flooding, have a homogeneous reservoir so CO2 doesn't channel right to your producing wellbore. And so again, reservoir characterization studies need to be done in great detail. In some of my slides today, I'll have a little bit of slant towards Colorado, but not always, simply because that's where I'm located. Sources of CO2 for EOR, of course, are the naturally occurring CO2 reservoirs. In the future, most likely to phase those things out. And then we have all of these other things that are listed on this slide, which could be sources for CO2 for the EOR purposes. So oil recovery volumes, this slide from Chevron illustrating under primary recovery, what the oil volumes are expected to be underwater recovery, the increase in the recoverable volumes, and then the incremental volumes associated with CO2 also then indicated on this particular diagram. So very diagrammatic, and I thank Chevron for putting this slide out on the web. And if there's a gold star on CO2 EOR in terms of who did it early on and continues to do it, I would give that gold star to Chevron for their activities. So the history of CO2 EOR, first large-scale operations in the 1970s in the Permian Basin. Since then, done around the world and under consideration elsewhere. Lots of different projects in the US and lots of CO2 usage and great increases in the volumes of oil recovered. So just a quick example of one of these projects that's gone on in the state of Colorado would be the Rangeley field of Northwest Colorado. Rangeley is located on the north side of the Douglas Creek Arch, real close to the Utah-Colorado border. And the field, the main reservoir in the field is the Weber Sandstone of Permo-Pennsylvanian in age. The initial well was drilled in 1933. Field development took place in the 1940s, which we'll talk about here shortly. So we'll visit about Rangeley. Rangeley is a very large structural field. The left-hand part of the slide shows a structural cross-section and a seismic line through the Rangeley area. There's also a diagram on the right, which shows the position again of Rangeley Field, and then some of the other Weber oil fields in northwest Colorado and northeast Utah. So Rangeley again is a very large structure, and the discovery well is indicated by the star right here, is drilled in 1933 by California company. Of course, that becomes Chevron. It IP'd for 229 barrels of oil per day. It produced 8,000 barrels of oil and then was shut in because of the remoteness of the area and such. It wasn't, the field didn't get developed in the Weber until 1943, which is toward the end of World War II, and that development occurred because of needs for oil and so on. So the area in consideration for this area, the scale is 1 square mile. I'm showing by my marker flashing around. So the total field, 31 square miles. The thickness of the reservoir, 250 to 300 feet. Depths, 5,000, 6,000 feet. The original spacing, 40-acre spacing, down to 20-acre, and there's also 10-acre pilots. Hydrocarbon column, gas columns indicated, the original oil in place, 1.9 billion barrels. Cumulative production also indicated in the EOR on this field, probably 1 billion barrels when all said and done. Original oil water contact, dashed blue line, original gas oil contact, dashed red line. Cross-section, which goes north-south across the field, illustrates the reservoir for the oil production. It's datum, stratigraphic cross-section, datum on top of the Weber. The scale indicated where my arrow is on this particular diagram. The Weber consists of a mixture of aeolian and fluvial sandstones. The aeolian reservoirs have better porosity and permeability than the fluvial section, and you can see from the darkened in bars, black bars indicate where porosity is greater than 10%, and that's where mainly in the aeolian facies. So the Weber, the age, it's an anticline, very large anticline, shows up at the surface, oil thickness, gas zone thickness, porosities, permeabilities. Source bed for the oil is Phosphoria formation. Weber sandstone, the initial pressure in the field, 2750 psi. Present pressure, because of water flooding and CO2 injection, over 3000 psi. Temperature gradient, the original drives within the field, and the well spacing also indicated on this slide. So water flood occurred from 1958 through 1986. Chevron initiated tertiary recovery in 1986 using CO2, but CO2 and water were pumped into the unit, alternating cycles, and so it's referred to as a WAG, if you will, water alternating with gas. At the surface, production streams separated into its various components, and then the CO2 gas, hydrocarbon gas, water are actually then re-injected back into the Weber. So this is a production curve, a little bit dated, but it suits the purpose for what I want to show, and that's the history of the field. The big development of the Rangeley occurred in what's called the Rangeley Boom from 1945 to 1950. Hard to imagine, but this little area in northwest Colorado probably at one time had about 50 rigs running in it all by itself because of that development activity. So the discovery, the development, hydrocarbon gas, reinjection into the gas cap, 1950 to 69, fields unitized, water flood expansions, infill drilling, 1958 onward. The CO2 WAG flood starts in 1986 to the present, 2000, 2011, renewed expansions and so on. And then of interest, perhaps original oil in place, primary recovery, secondary recovery, tertiary recovery. Tertiary recovery is actually a giant field all by itself, and you sum up all those numbers and close to 990 million barrels. So will we get to a billion? Well, time will tell, especially, and probably will because of new technology and so on. So initial decline, and you can see I've just put a dashed line on this production decline curve illustrating primary, also put a dashed line on what would have been recovered with secondary, and then you can see the incremental volumes that are recovered with the tertiary recovery. And pay attention to the scale down here and the colors for all these colors in the production graph. So the CO2 flood at Rangeley does and has affected the Weber sandstone from the Chevron people who published on this. Carbonate cements dissolved by the carbonated brine, and then the indications were the chemistry changes in produced waters indicated that clays and feldspars were also being leached. So those are some of the considerations when one does employ the CO2 EOR. So next to that, and the next topic would be CO2 Enhanced Gas Recovery, EGR, not really done, but is technically feasible. Gas displacement, pressurization of CO2 moves through the reservoir pore space, displacing methane in front of it. And this diagram from the Colorado Geological Survey in this article by Young et al. 2007 illustrates this idea of injecting CO2 into a gas reservoir, pushing methane to your producing well, and so on. So technically feasible. Underground gas storage fields are typically in three categories: depleted oil and gas fields, aquifer storage, and salt cavern. These underground gas storage fields store gas until it's needed during times of high electrical energy demand, and the gas is removed, but in times where that's not needed, gas is then re-injected into these gas storage facilities. And so this is a diagram which just illustrates those three, but also adds onto it mines and then hard rock caverns as a possibility. CO2 in underground gas storage fields, we have both a base gas and a working gas that's present within those fields. Again, gas is withdrawing during peak energy demands, and the fields themselves are generally converted from, many of them converted from depleted oil and gas fields. The working gas injected produced seasonally, while base gas is not extracted but is used for pressure support. So the idea here is to convert the base gas to CO2 gas, or eventually convert the whole field to a CO2 storage sequestration area. And just in the state of Colorado, just to illustrate where the existing gas storage fields are located, are shown by this diagram. And there's ones that's been decommissioned that's just north of Denver. The Leiden mine, which was a shallow coal mine, actually did work for many years. Public service company ran that, but urbanization, too many houses getting built too close to that facility resulted in that thing being decommissioned. So gas storage fields, again, this idea of the base gas and the working gas, and one of the ideas with CO2 would be to replace the methane with CO2, but have that as the base gas, and eventually maybe switching this whole thing to a CO2 storage facility. Enhanced coal bed methane recovery. Coal bed methane is an important resource. Coal seams source rocks, also a gas reservoir and a trap. Coal bed methanes form both biogenically and thermogenically. Methane molecules adsorb onto coal surfaces. They're absorbed in water. They also occur in free gas and fractures or cleats in the coal. Enhanced coal bed methane is a process by which carbon dioxide or nitrogens injected into a coal seam to increase methane recovery. CO2 has a much stronger affinity to absorb onto a coal surface than either methane or nitrogen. CO2 injected preferentially absorbed into the coal matrix and then displaces that methane for production. On the right-hand part of the slide just illustrates the adsorption isotherms for CO2, methane, and nitrogen. And the winner, if you will, who can absorb the most onto or the coal surfaces, again, would be the CO2. And the diagram on the left illustrates this concept of injecting CO2, adsorbing that onto the coals, displacing the methane, pushing the methane then to the producing wells. So a pilot was done using this notion just both for nitrogen and for CO2. Nitrogen was the Tiffany unit, CO2 the Allison unit, and this Allison unit ECBM field pilot had a number of coal bed methane wells, number of CO2 injection wells, volume of CO2 that was injected, and then incremental coal bed methane was actually recovered, amounted to something that could be considered to be quite economic then. This fairway just happens to be the best coal bed methane production in the San Juan Basin, so I don't want to confuse anybody with those colors associated with that fairway interval. So when we think about coal beds and enhanced production, there's a number of course, coal bed methane fields across the US and elsewhere around the world, and all of these would be suitable candidates for this enhanced recovery. Can also do geologic disposal of CO2 into coal bed reservoirs. Some of it can be in these deep unminable coals, probably from 2,000 to 7,000 feet. The 2,000 may be the lower depth for mining operations. The 7,500 feet is a depth where a lot of those cleats or fractures in the coal or overall permeability in the coals is sufficiently reduced that you may not be able to inject below those depths. So those, again, are very approximate numbers, but things to take into consideration. So you may have a magic zone here in which to inject the CO2 in deeper parts of the basin. So coal bed reservoirs for carbon storage have close proximity to the anthropogenic source of CO2, being our magic depth interval, and can be an area for lots of CO2 storage. Can also do enhanced shale gas recovery, also technically feasible, not being done because we have so much shale gas anyway. Similar to coal bed methane, enhanced recovery, inject the CO2 and displace methane then to the wellbore. There's also a possibility when we look at this of instead of doing fracture stimulation with water, use supercritical CO2 as more of the injecting fluid and so on. All sorts of issues, of course, both ways, which time does not permit to get into today. When we look at the abundance of shale plays in the US and Mexico and Canada and North America, they're abundant. And so this possibility of either CO2 storage or enhanced shale gas production can occur across very wide areas. Can also get into enhanced geothermal systems. Conventional EGS technology uses water as the injection fluid. CO2 is regarded by some as more favorable circulation fluid because its compressibility and expansibility includes injection of CO2 to enhance the efficiency of re-injecting hot water by improving porosity and permeability through water rock reactions. So we're down there dissolving perhaps some of the carbonate or feldspars and so on within that rock. Injecting CO2 in hydrothermal or hot rock reservoirs can maintain reservoir pressure and can also promote flow rates of in situ water back to a production well. So either use pure CO2 all by itself or this combination of water and CO2 in this overall scheme. So the enhanced geothermal diagram right here would be for water injection. So water injected in 0.6 right here, and then these hot fluids come back to the surface in 5. The production wells go to the heat exchanger and generate electricity and so on. There's also the idea along the lines of geothermal systems of doing the CO2 plume geothermal, CPG. CO2 plume geothermal involves injection of CO2 as a working fluid to extract heat, pressure energy from high permeability sedimentary layers. Injected CO2 forms a large plume, absorbs heat from geothermal reservoir, buoyantly rises to the surface, drives power generation, and so on. CO2 then is cooled and recycled into the underground systems. So CO2 is injected. You have this CO2 plume that forms because of the density differences. It is buoyant, rises to the surface. As a geothermal heat energy, it also becomes quite warm. CO2 goes back to the surface, turns a turbine, generates electricity, goes to a cooling tower, either CO2 from pipelines or from that cooling tower, re-injected into the subsurface and so on. So pretty new, but the CO2 plume geothermal concepts, which are now being articulated. And then the topic which is happening a lot, the deep saline aquifers, saline geologic formations, contain pore water too saline for water supply, too deep to be economic. You do want to have good aquifer, want to have good reservoir properties, porosity, permeability. You want to have a large areal extent, so the volume of CO2 that you're injecting can be significant. Most CO2 point sources, that is power plants, have a saline formation at some depth beneath them, and we are experts at injecting industrial waste into the subsurface already, and so we have an infrastructure and the knowledge on, of course, how to do this kind of injection into saline aquifers. So the criteria to select the water-bearing formation, a lithology, a lot of them are sandstone, but they can be, of course, carbonate too, other types with, as long as they have porosity and permeability, want to exceed our depth of 3,000 feet, want to have high salinities, critical to have a good top seal, be good to have stratigraphic or structural trapping mechanism to decrease the possibility of migration of the injected CO2. Supercritical CO2 is used. CO2 initially stored as a gas phase in the specified brine, and then part of it can be stored over time as dissolved gas phase, and then over time CO2 is stored as a residual gas phase, and over a long period of time some of that CO2 causes precipitation of carbonates and so on. So just the diagram of an injection well, having a good seal into some sort of an accumulation, showing it as a sandstone here, but supercritical CO2, there will, the boundary of this plume, if you will, be some dissolve. Some of the CO2 does get dissolved, of course, into the brine. So the CO2 trapping in the subsurface over time since injection stops, diagram that probably you're familiar with, but initially structural stratigraphic trapping, and then get into residual CO2 trapping, solubility trapping, and eventually, after many years, perhaps 1,000 years, mineral trapping. And little cartoons of each of these is on the right-hand portion of your slide, the residual, residually trapped CO2, the solubility trap CO2, and then the mineral trap, which is probably more of the permanent trapping, as long as we don't have another phase of CO2 that comes through and dissolves out that carbonate. And initially all trapped either structurally, stratigraphically, or injected in some other structural situation in the subsurface. This is a map showing projects of injection or having injected CO2 into deep saline aquifers. I just show it because before I mentioned the Rangeley oil field for EOR, so just wanted to point out where that is again. And as example of CO2 injection into deep saline aquifers, we'll look at this Schleppner field from the North Sea. So if there's somebody that gets a gold star for deep saline aquifer injection, my gold star, you can have your own gold star, whoever you want to give it to. I'd give it to Statoil Equinor because they're definitely leaders of doing this. And this one field, Schleppner in the North Sea, they've been doing it for many years and also monitoring it over time. So this field offshore CCS project, since 1996, it's been used for carbon capture storage by Statoil Equinor. Million metric tons of CO2 is captured, stored per year. Project summary reports the possibility of 600 billion metric tons capacity. The injected CO2 here is in the Miocene Utsira formation through a dedicated well. Deltaic sands sealed by clays. They've used time-lapse gravity and seismic methods to monitor what's happening in the subsurface. So this CO2 injection into the Utsira formation at Schleppner. Schleppner is a gas field that produces out of this deeper formation that has about 10% CO2 gas in it, and the needs then were to do something with that CO2 gas. So they adopted this idea of injecting it into the shallower formation, the Utsira formation. And the deeper Schleppner west and east fields have reserves that are quite significant of both gas and condensate, and the needs came up for doing something with that CO2. So the work has been done, injection well in this Utsira formation, and then it's been monitored by Statoil Equinor over time. The injection into these deltaic sands, overlying seal, underlying seal, and then you can see the development of the CO2 plume, if you will, over time into a number of separate layers, and that periodically gets republished by Equinor and others. I'll move on to the next topic, which would be geologic disposal and natural CO2 fields. Natural CO2 fields are currently the major source for CO2 in EOR, but let's keep in mind CO2 also is used in a variety of other ways: welding, manufacture of dry ice beer, growing plants, food, beverage, industry, et cetera, et cetera, et cetera. So CO2 actually does have lots of uses, EOR, plus a bunch of other things. In the greater Colorado area, the Paradox-Raton Basin, CO2 naturally occurring is used for EOR projects in the Permian Basin, and there's over 50 of those projects, existing pipelines, infrastructure going to the Permian Basin. The idea would be to not use the naturally occurring CO2 in the future, but using anthropogenic CO2 instead of the naturally occurring CO2. So the deposits themselves provide a low cost of CO2 for EOR projects. Large CO2 fields actually are useful analogs, though, for evaluating safety and costs of geologic sequestration. So they already exist. what's unique about them, they have some kind of container, excellent seal, and so on, and they've had a long-term physical trapping then of that CO2. There's a lot of industry field experience in handling and transporting large volumes of CO2. So natural CO2 accumulations around the world are extensive. There are some which are close to 100% CO2, or many that are in this 50 to 100% by volume CO2, and then some that are 5 to 50% of CO2. And a lot of times that CO2 is, again, used for a variety of purposes. In the future, the idea would be to perhaps convert those natural CO2 accumulations, instead of producing it, inject right back into those reservoirs. So to make that more of a storage facility. Then the last topic that I'll get to is just this mineralization in our brief discussion today over your lunch hour. Carbon dioxide carbonation of silicate minerals, mineral CO2 sequestration focused on olivine, serpentine, wollastonite, minerals rich in magnesium and calcium, mineral silicates found in mafic, ultramafic rock, and industrial sector of coal fly ash, municipal solid waste, incinerator bottom ash, asbestos waste, mineral slag. So we find these mineral silicates in a variety of areas. Also, brines associated with oil and gas extraction have a potential of cations, especially calcium, for mineral carbonation, in other words, making carbonate. So a cartoon then, if you will, of this mineralization concept, injecting or using things at the surface to actually create carbonate rocks and so on. And one of my last slides just illustrating this idea of some sort of a power plant generates a lot of CO2. CO2 is piped then to a carbonation plant, mineral carbonation plant. We do a magic mix of serpentine, olivine, and so on in this plant, and then have this waste product of carbonate material and silica material that can be used in construction, mine reclamation, and for other purposes. Some important mineral reactions associated with serpentine, olivine, and wollastonite, making carbonates, of course, and perhaps some silica as a residual, but those would be the reactions, and lots of others that are possible too. Of interest to you would be this website, which illustrates US early stage. It's an active website. And so you can click on any of these things, find out greater detail about any of these circle areas, early stage CCUS project map. And so some direct air, industrial power, storage sectors, geologic formations, where are all the saline aquifers, and so on. What's the size? Very useful website, perhaps. So in today's brief discussion, I've gone over the geology disposal of CO2, the storage or sequestration, however you want to term that. We briefly touched on everything on this list, kind of went over some of the list and illustrated just a few examples in the course. If you elect to take that, we'll take a much deeper dive into each of those examples that I kind of went through in a fast fashion. So with that, I'm going to call it good and turn it back to Susan. Probably talked too long already. She didn't give me quite the hook, but
thanks, Steve. That was a whirlwind tour, and we've already gotten some questions that have been coming in through the Q&A feature on the webinar, so let's get started. Can you model the type of particles that might leach as a consequence of CO2 injection?
Can you model the type of leaching that can take place?
I think this was before you got to the mineralization part, so this was kind of early in the webinar.
All of these reactions can be modeled in the laboratory and are modeled in the laboratory and also then field tested. So the outdoor laboratory, the indoor laboratory, all of these things can be not only physically set up experiments, but then you can also do experimental modeling too. Yes, I guess would
Okay.
be.
Next question, what would be the ideal well pattern design for CO2 injection to optimize oil production?
CO2 injection to optimize oil production?
Right. Peripheral 5-spot, inverted 5-spot.
Oh, if that's what you mean. Well, I'd go back to models like Rangeley Field and see exactly what they've done. And I know a lot of the water injection patterns started out as line drives, all evolved to 5 spots. And I think when we start looking at CO injection, and keep in mind the CO2 injection is generally the WAG, so water alternating gas. And so it could be a 5-spot. And when you do the volumetrics and so on associated with what is your recovery going to be from a 5-spot perspective anyway, pretty easy to calculate volumes, injected volumes, how much pore space are you using and so on for the CO2 in the water. So I guess my short answer would be we have a lot of great examples, Weyburn Field in Canada, and we perhaps will take a deeper dive into that in the course coming up, and then the Rangeley Field too. And the operators have already illustrated what the ideal drilling patterns are, or I should say over time it's been modified such they think they're at the ideal pattern right now. And so there's an evolution of development, well spacing, and so on when you get into these operations. And you could see a little bit of that, sorry to make a short answer into a long answer, but the production curve at Rangeley, you saw all these bumps up and down with the oil production. And quite honestly, Chevron was changing what they were doing in that development of the field, changing from 40-acre spacing to 20-acre spacing to 10-acre pilots to injection, changing from line drive to 5 spots, and so on. So I still give them the gold star, but keep in mind it's something you're going to be developing over time, I think.
The next question, the natural CO2 accumulations, how do they occur? Are they a supercritical fluid? And if so, generally in what types do these CO2 accumulations occur?
So I left the slide out, of course. Generally, it's close to magmatic sources in the subsurface, and that CO2 then has migrated into fields, Bravo Dome, or McElmo Dome, or other, in the state of Colorado anyway. They can be at depth, which would be sufficient pressure and temperature to be in a more of a supercritical state. That's actually an excellent question. And the gases themselves then brought to the surface. So the phase diagram and such, and the pressures on some of those fields are also in the published literature, which would then indicate whether they're in a liquid or a supercritical condition. But keep in mind, CO2 is moving around from this gas to liquid to supercritical state, and the supercritical state has a density like a liquid but behaves like a gas. So anyway, it's my answer, and I'm right now going to stick to it.
Thank you. We have some more questions, but I'm going to go ahead and make closing comments for those of you who need to leave at the top of the hour. Thank you for attending today's webinar. Later today, you'll receive a link to the recording of the webinar, an evaluation form, and a link to register for Carbon Capture, Utilization, and Storage, a Geologic Perspective, scheduled for April 25 through 29 in live online format. So a couple more questions. What is the average volume of CO2 injection per well and the pressure to increase the production? How do you expect to see results? How soon do you expect to see results?
So those specifics, which is kind of funny, I had slides which showed those specifics associated with
Those will
Rangeley
be in the
oil field.
class.
And because of the length of my talk already, I left all those sorts of slides out, but that's been published. What is the volume that's required? And then you're already getting a response. You probably are injecting CO2 if you're doing EOR into a field where you've done water flood, so you're already seeing a response. But then you're going to start seeing more of a response, and you have to kind of go back to the production curve at Rangeley Field, and the overall flattening or uptick of production occurs fairly fast. Now, is that fast enough? You'd say you inject it this week and you're seeing a response the following week in your producing well. I guess the answer there is maybe, maybe not. So it's over time you'll actually see this response, but it's fairly short time interval. And the increase in production associated with CO2 shows up at the Weyburn production curves, and then also at Rangeley and other EOR projects.
Next question, what are anthropogenic sources of CO2 and how are companies capturing CO2 today?
So that was covered on one of the slides, which I didn't go list down, but there's all sorts of places that we're generating CO2. And unfortunately, perhaps going into the atmosphere. So there's a whole variety of those, mainly industrial sources and such. Some of it's related to oil and gas activity, but we're trying to encourage everyone to completely minimize that. And can you remind me what the last part of your question was again? Sorry.
How to find sources of CO2?
Say that again.
How can you find sources of CO2? How are companies searching for sources of CO2?
They're coming off of coal-fired power plants. I mean, the CO2, I hate to say this, but CO2 emissions are occurring in lots of different activities. So finding it perhaps is not that.
It's the easiest challenge.
That may be the easiest challenge. I think one of the more interesting concepts, which is happening now, is this direct air capture of CO2 by Oxy, Chevron, and others in places like the Permian Basin, where they're actually trying to remove CO2 from the air, capture it, and then inject it into the subsurface. So I guess we have abundant sources of man-made CO2 already, and what we're trying to do is be good stewards of spaceship Earth and minimize all of that and capture it and put it into the subsurface.
Class 2 injection wells have been around for decades. How come Class 6 injection wells have been so slow to permit?
Well, the class, kind of like in the state of Colorado, Class 2 are run by the state of Colorado Oil and Gas Conservation Commission, and Class 6 are not yet regulated by the Oil and Gas Conservation Commission in Colorado. So Class 6 is more of an EPA regulated.
Different agency.
It's a different agency, but the future would be where those most likely, and I'm just going to say this, time will correct me on this, but they'll probably all be regulated by the oil and gas commissions in various states, in cooperation with the EPA, of course, Class 2, Class 6.
How often does CO2 injected for EOR actually leak? If rarely, then there's little advantage to mineralization compared to injecting in developing sedimentary reservoirs. I think that's a question.
So leakage of injection of CO2 into the subsurface, one of the primary concerns is leakage. And the way to get around the leakage is proper reservoir characterization up front, making sure seal integrity and so on, maybe early seismic surveys to make sure you're not injecting right next to a major fault system and so on. So leakage could occur. From the physical standpoint of drilling, injecting, and so on, I think suffice it to say that proper well design should be able to prevent that kind of leakage from occurring. But careful monitoring of CO2 pipelines, careful monitoring of the fields themselves is quite important. And so that is an activity that needs to take place. Just like fields these days are being monitored for methane leakage, or areas are being monitored, same happens with CO2. And then if there is a identified leak spot, fix it.
Absolutely. Well, thank you for your time today, Steve. We've had some wonderful questions. I want to remind everybody you'll receive a link to the recording of today's webinar and evaluation form, a link to registration details for carbon capture, utilization, and storage, a geological perspective, scheduled for April 25 through 29, live online, brought to you by SCA. Thanks for joining us today. Goodbye.
Thank you all. Bye-bye.